Hello, young physicists. Have you ever wondered why a swinging pendulum keeps moving back and forth like a metronome, ticking time perfectly? Here's a quick joke to start. Why did the pendulum go to therapy? Because it couldn't stop swinging between extremes. Now, let's break down the simple pendulum in the clearest way possible. Picture a tiny point mass. Imagine a tiny bob or a small metal ball hanging from a string that has no weight itself and does not stretch. This setup forms the classic simple pendulum. It swings back and forth under the pull of gravity, like a playground swing but simpler. The motion isn't just any movement, it's angular displacement from the vertical line, meaning we measure how far it moves sideways in degrees or radians. For small swings, where the angle theta is much less than 1 radian, that's about 57 degrees or less, the pendulum's motion repeats itself perfectly in cycles. This is called periodic motion. The force that pulls the pendulum back toward the center isn't random, it comes from gravity creating what we call a restoring torque. This torque acts to bring the pendulum back toward its lowest point and is proportional to how far it's displaced angularly. Mathematically, this restoring torque is given by tau equals minus mg L times sine theta, where tau is torque, m is the mass of the bob, g is acceleration due to gravity, L is the length of the string, and theta is the angular displacement. The negative sign means the torque works opposite to the displacement, always pulling it back. But here's the beauty, when theta is very small, sine theta is almost equal to theta itself in radians. This tiny simplification means the pendulum behaves almost like a perfect simple harmonic oscillator, and its motion follows the neat rules of simple harmonic motion, or SHM. So, starting with a practical model, we've set the stage to understand the pendulum's dance, the timeless, swinging back and forth under gravity's watch. Let's dive a little deeper. Don't worry, it won't be scary. Remember, our pendulum swings because of a restoring torque, and this torque causes angular acceleration, which makes the pendulum speed up or slow down as it moves. The torque tau equals the moment of inertia I times angular acceleration alpha. For the pendulum, the moment of inertia I is mass m times length squared, L squared, since the mass is concentrated at the end of the string. Using the small angle approximation, the torque is tau equals minus mg L times theta. Plugging this into our torque equation, we get ml squared times the second derivative of theta with respect to time equals minus mg L times theta. That means the mass times the square of the length times the angular acceleration equals minus the mass times gravitational acceleration times length times angular displacement. Now, to simplify, we divide both sides of the equation by ml squared. The mass and one length cancel out, leaving the second derivative of theta with respect to time plus g over L times theta equals 0. This equation is the classic form of simple harmonic motion. Written out, it looks like this. The second derivative of displacement plus omega squared times displacement equals 0, where omega is the angular frequency. Here, omega equals the square root of g over L. In simple words, this means the pendulum's angular displacement behaves just like a spring oscillating back and forth. It follows simple harmonic motion with an angular frequency determined by gravity and the length of the pendulum. So, how long does it take for the pendulum to swing back and forth once? That's called the time period. Note it as t. Think of it as your pendulum's beat or rhythm, the time for one full to and fro swing. Since the pendulum follows simple harmonic motion, the time period t is related to the angular frequency omega by the formula t equals to times pi divided by omega. Putting that in words, t is to multiplied by pi divided by omega. But from before, omega is the square root of g over L, So flipping that and substituting gives us the neat formula T equals to times pi times the square root of L divided by G. What's amazing is that this time period does not depend on the mass of the bob. In other words, whether you hang a big rock or a tiny ball, the timing stays the same. Also, for small swings, it doesn't matter how big the angle is, the time period remains the same. This is why pendulums were historically used in clocks. Their timing is so reliable. Plus, this formula gives a good approximation even for physical pendulums, which have extended masses instead of point masses, just with some adjustments. Let's talk energy, shall we? A pendulum always has energy, sometimes stored, sometimes moving, kind of like you when you're on a swing set. At the extreme positions of its swing, where it momentarily pauses, the pendulum's potential energy is at its maximum. This potential energy can be expressed as mgL times 1 minus cosine theta, where theta is the angular displacement from the vertical. As the pendulum passes through the lowest point, all that potential energy converts into kinetic energy, a kind of energy of motion, given by 1/2 mv squared, where v is the linear speed of the pendulum bob. Throughout its swing, the total mechanical energy stays constant, meaning the sum of kinetic and potential energy doesn't change, energy converts back and forth smoothly. This total energy equals mgL times 1 minus cosine theta maximum, where theta maximum is the farthest angle the pendulum swings. This beautiful exchange between kinetic and potential energy makes simple harmonic motion possible, with a continuous and smooth transformation of energy from one form to another. Now, things get a bit more interesting in the real world. A pendulum isn't swinging forever in your school lab because of damping. Forces like air resistance and friction at the pivot slowly steal energy away, causing the swings to get smaller and smaller over time. Also, our trusty small angle approximation, that sine theta approximately equals theta, only holds if the swing angle is small. When the pendulum swings wider, this approximation breaks down and the time period formula we love becomes less accurate. In fact, the time period actually increases a little for large swings. For systems where damping matters, like in real life, the amplitude of oscillation decreases exponentially with time, often described by amplitude at time t equals initial amplitude times e to the power of negative bt, where b is a damping coefficient. So, the pendulum slowly loses energy until it finally stops. Understanding these limits helps us see why clock pendulums have small swings and why real oscillations differ a bit from the perfect theory we studied. Let's put theory into practice with a simple calculation. Imagine you have a pendulum of length 1 meter and we take g, the acceleration due to gravity, as 9.8 meters per second squared. We want to find its time period t using the formula t equals to times pi times the square root of L divided by g. We substitute in the numbers length 1 meter divided by 9.8 meters per second squared. Taking the square root of 1 divided by 9.8 gives us approximately 0.319 seconds to the half. Multiplying by 2 pi, around 6.28, we get about 2.005 seconds. Rounding it nicely, the time period is roughly 2.01 seconds. This matches well with what you'd see in a physics lab when timing a 1 meter pendulum, proof that the theory syncs beautifully with reality. Let's wrap things up. Remember, the time period t of a simple pendulum equals to pi times the square root of length over acceleration due to gravity. The angular frequency omega equals the square root of g over L, and the motion satisfies the differential equation where the second derivative of angular displacement plus g over L times angular displacement equals 0. Energy-wise, the potential energy at any point is mgL times 1 minus the cosine of the angle. The key takeaway is this: At small angles, the simple pendulum undergoes simple harmonic motion with a time period independent of the mass. We derived its motion equation from the balance of torque and inertial torque, applying the small angle approximation. Energy continuously converts between kinetic and potential forms, while total mechanical energy stays constant. Keep in mind, damping forces and large angular displacements change the picture, affecting the period and energy transformation. That's it for today's concept. Remember, physics is more fun when you can laugh and learn together. See you in the next session and keep swinging with curiosity.